Well, welcome to our circuit. As you can see, we have the NXT block mounted on a car with an arm that swings in an arc, as well as a bay of photoresistors that establishes an XY grid, each hooked up to individual resistors and a lab jack. The lab jack takes its reading in between the resistors and in between the photoresistor and ground. Now, as you can see, we have beautiful breadboarding done by our own Caitlin. It is absolutely the most gorgeous thing I've ever seen. And this allows us to take each of these photoresistors acts as a voltage divider. It allows us to take readings across them. When the LED is over the photoresistor, the voltage across the photoresistor goes down, allowing us to know where the LED is actually in the XY grid.
So this is our LabView code, and as you can see, it's in an overarching sequence structure first. So it runs this portion of it very, very first. So what we have it do is move our motors so that the arm moves backwards and over so that it hits the first array, like that. Then after that, what happens is it goes into this second sequence. In the second sequence, we have a lot. We read from the lab jack initially, and then that goes out to both a numerical indicator and a waveform chart. Then it gets compared by this comparator with our known value of 4 volts, which is about our threshold for when the LED is over it. Based on whether it's true or not, it goes into a Boolean, which lights up in our LED array, and then it gets converted into a 0 or a 1. We take those, and each of our 13 gets multiplied by its corresponding number, and those 13 all get summed up. So while 1 will be true, the rest will all be 0, and we will have the number of the LED that's on. This comes out in both a numeric indicator and goes into a case structure. For all of our cases, it has a corresponding motor action that tells the NXT, our little car, exactly what we want it to do next. At the same time, we have a lovely graph being made that plots all of these points and has another case structure that goes through and tells it which point is being hit every time this specific number comes into it. And those are all graphed live on our lovely XY graph.
Let's first take a look at the front panel. As you can see, we have a display of 13 waveform charts. This gives us an idea of the voltage drop across each resistor. They correspond to each photoresistor in our bay of XY photoresistors, as well as indicators giving the value of each voltage drop across each photoresistor. If we scroll down, we will see a LED grid that shows which LED or which photoresistor has the LED on top of it, as well as a graph, XY graph, that traces out the movement of our LED in the grid. Let's take a look at the movements of our car and the LED. The car starts in the up position and moves to the first photoresistor, and then finds the next. Right now is searching for a photoresistor and using its toggle ability. This allows for less calibration as well as more versatility. Here again, the car is lost and waiting to find a photoresistor. And it's going to get there. And it's continuing to follow the spiral pattern we designed it to follow until it eventually reaches the center and now resets. As you can see in the front panel, it drew a spiral pattern within our graph, and now it's starting over. it will continue to run until we hit stop. At the same time, you can see it when the LED or when the LED is over the photoresistor, it'll light up the LED in our front panel, giving us an idea of what is turned on. And again, we're doing nothing to the car, not touching it ever. It is just continuing to run its pattern. I could let this video sit here for 10 minutes and you would see the exact same thing in 10 minutes. We have actually tried this before. And again, it finds the center, resets, and goes again. Let's watch one more time through, just for the fun of it. The most impressive thing about this was the toggle ability. This allows us the ability to do any type of pattern, and the calibration doesn't have to be dead on. And we make it to the center, and we reset. And here's the cool pattern our NXT block has drawn.
And here we have our circuit diagram. You can see it's a very simple, just voltage divider with the positive voltage and the ground on either side of our two resistors. The big complication is there are 13 of them. And so you have our 13 photoresistors on the side and our 13 33K ohm resistors on the side, with the lab jack taking a reading in between each and every one of them, which is why we had to have 2 lab jacks.
This is Kyle coming back to the lab to check on my NXT brick. We've let it run for about 10 minutes without us touching it at all, and look, it's still running. It's still getting to the center. That's the amazing part of our design. And here it goes. And after 10 minutes, it still reaches the center and resets itself with no human interaction whatsoever. Looking at our project, you would be surprised to find out one of the most difficult things about it was the calibration. Before this project, Caitlin and I never knew how precise electronic calibration can be. The voltage ranges were difficult, the exact movement was difficult, but if we run our code, the biggest advantage we figured out was the toggle ability we discussed earlier, as seen there. This allowed us to tackle the calibration.
So a big part of our project was the interfacing circle. So what we had to do was come up with a way to have a circuit board be redirected into the computer, have it process something, and then tell the circuit to keep doing something. So what we have it do is we have it read the photoresistors from the LED on our car, and then be read by the lab jack, which tells our computer exactly where our LED is, and then that in turn tells the car where to go next, thus creating our interfacing circle.